Okay, so welcome back everyone. So let's start our next lecture. So Rick Kenyon will continue his lectures, limit shapes and variational principles. So welcome, Rick.
Thanks, Vadim. Welcome back. Thanks for coming back. I wanted to start with a little announcement. As you hopefully you see on your screen here, there's a conference which starts next week. It was originally a 1-week conference, but we extended it to 2 weeks with just a few talks per day, 2 or 3. And well, if you need any information, it's okay. It's all about dimers in combinatorics and cluster algebras. Organized by myself, Greg Musiker, Sebastian Franco, Dave Spire, and Lauren Williams. So dimers is as you know, a fairly large area now involving a lot of intersections with combinatorics and integrable systems and string theory and so on. So let me go to here. All right, how's that? Can you see that screen there? So this is where we were. I want to talk today about some general facts about gradient models. Last time we talked about some specific variational principles for random surfaces and random curves, which gave rise to a certain variational principle, and today I want to discuss some general properties of these kind of variational principles for surfaces, 2-dimensional surfaces in R3, graphs of functions from R2 to R3, R2 to R. And this is something that involves some very old theorems going back to Ampere, but also we realized some new ideas which were inspired by our work on the 5-vertex model, the dimer model, and the 5-vertex model, which I'm going to talk about on tomorrow. So, and I hope you're not. I know most of us are not geometers, so I'm going to try to explain as much as I can. But nothing is very complicated. I hope it's all just some calculus in the end. So let's get started. Here's the general kind of variational problem we're trying to solve. We're looking for a fixed function h. We have a region R in the plane, right? X and Y are the coordinates in the plane. R is some closed region, and on the boundary of R, we have some fixed Dirichlet boundary conditions. And we're looking for a function h, which minimizes this surface tension integral. And the important fact today is that it's a gradient model in the sense that the surface tension only depends on the gradient of h, the slope of the surface. Other models where you include gravity or whatever are not going to fall into the context of today's talk. All right, and just for simplicity, we're going to assume that the surface tension is smooth, strictly convex, and in fact, we're going to need a slightly stronger condition, a certain uniform ellipticity in the interior, certainly ellipticity condition in the interior, but I'm not going to worry too much about that. It's a mild extra condition. And okay, but the surface tension doesn't have to be defined on the whole plane. It in principle can be defined on just some subset of the plane. And maybe N should be a convex region with interior in the plane. We can always extend the surface tension to be plus infinity outside of that region, and then it'll still work out. It just means that the set of allowed slopes may be some bounded set, just like in the previous pictures we had where the surface tension was only defined on a triangle. Okay, now the first thing to point out that was not obvious before is that there's a natural Riemannian metric on n itself. And this metric arises from the Hessian of sigma, right? The matrix of second derivatives of the surface tension sigma. So sigma is going to be coordinatized by these two coordinates s and t. S and t are coordinates on n. Right, so the Hessian of sigma is this 2 by 2 positive definite symmetric matrix, and that gives rise to a Riemannian metric G. And so here's the sort of typical diagram for the Lawson's tiling model. N is the unit triangle here, and but then the gradient of sigma maps the interior of n onto this other plane, this xy plane, and the region, the image is called the amoeba. So the amoeba, by definition, is going to be the image under a gradient of sigma of the interior of n. And in the case of the Lawson's tiling model, it's an exact sort of algebraic amoeba, which has a well-known definition, a well-defined meaning in algebraic geometry is the image of a certain algebraic curve under the logarithm map, under the log map from C2 to R2, where you just take the logs of the logs of the moduli of the coordinates. But we can just define the amoeba in a more general setting to be just the image of n under the gradient of sigma. And likewise, there's the free energy F is a map which goes the other, is defined on the xy plane, and its gradient goes the other way. So that it's the Legendre dual of the surface tension. So there's this interesting duality between these two sets. And if you use the Hessian of F, you do the exact same construction. You in fact get another metric over here, but this map is an isometry between the two. So there's really only one metric space involved in these two pictures, which you can coordinatize in either way on the left or the right. Okay. So now going back to Gauss, this is, of course, the oldest theorem here. I think that there is, whenever you have a Riemannian metric on a two-dimensional surface, smooth Riemannian metric, there's a certain so-called conformal coordinate, and I have to sort of explain what this means. But it's a coordinate z. If you like, you can think of z as a diffeomorphism from the domain n, or the amoeba, to some new domain, which somehow takes the metric to these u and v coordinates, in which the metric has this diagonal form, some constant times du squared plus dv squared. A scale of the Euclidean metric. However, the scale factor can, of course, vary from point to point. And so maybe what I wanted to do, is just indicate this with a picture here. So on our triangle there, we have a certain, right, this is, okay, this wasn't very good. Let me try again. My computer is being hesitant about drawing these things. On this triangle, we have a metric, which means that at every point we have if we draw a little ball of radius epsilon, it looks, from our Euclidean perspective, it looks like an ellipse, right? The ball of radius epsilon is an ellipse at every point, and that ellipse has a certain eccentricity, has two major axes and a minor axis, which vary from point to point. And the point of this conformal coordinate is that it's mapping the domain n here to some new domain, let's say the upper half plane here, h. And it's a diffeomorphism which will straighten out all those ellipses simultaneously. So each ellipse each infinitesimal ellipse over here becomes an actual round circle on the right-hand side. And of course, so this is just a sort of a linear condition, a local linear condition on Z, which on the diffeomorphism Z has to straighten out all these ellipses. And if you write down the sort of the appropriate calculation, that leads to this this equation here, that the Z, this diffeomorphism, it's simpler if you write it in complex coordinates. So ZS plus IZT over ZS minus IZT has to be this particular quantity mu, which is called the Beltrami coefficient, which is some coefficient you can construct from the entries of the Hessian matrix or the entries of the metric. Okay. Does that make sense? So anyway, this is the equation which Gauss set out to solve, and he showed that there's one can always solve it, and of course, once you pick the image domain, the domain of Z, then it's well defined up to conformal automorphisms of that domain itself. Okay, so in our case, that's the Beltrami equation, which we need to solve. Z is the unknown here, and all this stuff is given to us. The right-hand side is given to us. And of course, you can just, this is equivalent to ZS over ZT being equal to a certain complex number over here, which is again, just, this equation is just that one, a simple manipulation from the previous one. But now, I'm just going to do a tiny bit more little calculus manipulations here. If I look at XZ, what I want to prove this equation here, that this equation here is equivalent to that one, and it's just a little bit more work, right? XZ over TZ. If you remember what capital X is, well, maybe I should remind you what capital X is, right? Remember that X and Y are the conjugate coordinates. Oh, that's still supposed to be a T. Conjugate coordinates to S and T. So that X is the derivative, the S derivative of sigma, and Y is the T derivative of sigma. All right. So then, but there's this interesting and somewhat mysterious relation between X and T and Y and S, which is that the derivatives, the Z derivatives of XZ over TZ and YZ over SZ satisfy this interesting equation involving the square root of the determinant of the Hessian. And you just derive this just like a one-line derivation here, right? Sigma S sub Z, you expand using the chain rule here, sigma S SZ, sigma ST TZ, right? The TZs here cancel and you get the first term here, and the SZ over the TZ, right? So sigma SS is this guy, and then SZ over TZ turns out to be this. SZ over TZ is related to ZS over ZT by some sort of inverse derivative. Right, if you want to know the Z derivative of S divided by the Z derivative of T, then you can get that from the S derivative of, right, anyway, Z and S, using the inverse function rule for derivatives, you can convert that, you can convert this thing into that thing there. That's what comes out. And of course, if you expand this out, I think if I didn't make a mistake, if you expand this out, then you get that, then you get the previous, at least you get the left-hand equation here. And you can do the similar thing for the right-hand equation. Okay, so there's nothing really mysterious going on this slide, except for that first equation, how to solve that equation. And Gauss actually showed that this complicated looking PDE can actually be solved with can be converted into an ODE, and therefore you can just use the existence of solutions to ODEs to solve this one. All right, there's one further step which I didn't feel like I needed to further bore you with more derivatives, but this is a theorem of Ampere, also extremely old, almost 200 years old, which is that in this setting, the Euler-Lagrange equation, if you remember what the Euler-Lagrange equation was for our minimal surfaces, for minimizing surfaces, had this very simple form, x, the little x derivative of capital X plus the little y derivative of capital Y equals 0. Well, you can combine this with the mixed partials equation, you know, hxy equals hyx, where h is the height function, which in this form, right, is just sy equals tx. Those combine in some sort of magical way into a single equation of one complex variable, z. So here, this coordinate z really is the magic coordinate because it allows you to combine these two real equations into one complex equation. This is a complex multiplication now, xz times zx plus yz times zy equals 0. Well, you can kind of see how this relation is related to this one, except that if you expanded out the Euler-Lagrange equation by using the chain rule, you would also get a z-bar term. But it turns out that the z-bar parts are equal to the z parts, and so really this is what it ends up being. Okay, so that's very, very nice. This is a first order PDE for z as a function of x and y, and the coefficients here, however, are, you know, potentially complicated functions of z and also z bar. You know, so it's, even though it's a first order PDE, it's not necessarily, you know, simple to solve still. However, there's one more simple trick, which is to invert the dependent variable and the independent variable. So now if instead of thinking of z as a function of x and y, we can think of x and y as functions of z. And then, you know, so here, if I just, this equation here is the derivative of z with respect to z bar, expanded out using the chain rule with respect to x and y. So zx times xz bar plus zy times yz bar equals 0. That's just the z bar derivative of z equals 0. And this allows you to rewrite this ratio of zx and zy as a ratio of yz bar and xz bar. So that equation there becomes this equation here. Again, assuming I didn't make any mistake, this is now an equation for x and y considered as functions of z and z bar. But now the interesting thing is that the denominators here, or the coefficients here, capital XZ and capital YZ, they are independent of, they don't, little x and little y do not appear in those denominators. So this is just a linear equation. It's a linear equation for x and y if you consider them as functions of z. It's a linear first order differential equation for x and y as functions of z. In particular, because it's linear, solutions form a vector space. If we have one solution, if you have two solutions, we can add them together and get a third solution. And we can take a solution and multiply it by a scalar and get another solution. That's something we didn't have before in the inverse coordinates. And it's funny to think about minimizing surfaces as satisfying some sort of linearity, because how do you add two solutions, add in quotes, two solutions to get a new solution? That's not a completely obvious thing. So what you have to do is, let's see. I'm thinking about here, maybe I can go back to the whiteboard and draw a picture. And let me change my pen to black here. So it's hard to draw a sketch in 2 dimensions, so let me just go down 1 dimension. So suppose this is, well, okay, so I'll make some attempt. Suppose this is one solution. The solutions are always saddle shaped because they're minimizing. There's one solution and I want to sort of add, in some sense, some other solution, right? I don't know how to draw a surface. How do you draw a saddle-shaped surface? Okay. What you do is you for each point on the first surface, you look at the normal vector, and you find the point on the other surface with the same normal vector, there, the unit normal. And then let's call this point P, and that point P prime. And then you make a new surface which is located at the point P plus P prime. P and P prime are just points in R3 here. Everything is taking place in R3 here. You can add the 2 points together, and you make a surface whose normal vector at P plus P prime is equal to that normal vector there. So it's kind of like a Minkowski sum of these 2 surfaces, and that gives you a new limit shape there. So this new surface is composed of summing together points on the surface with the same normal vector. And of course, you might object that this surface may have several points with the same normal vector, but it's really a local operation. So if you start P and P prime near here, and then you start varying the normal vector, you're going to get a little patch, and then you sort of analytically continue to a patch around here. Does that make sense? I lost my, okay, there it is. No, I didn't. Where did, oh, wait. I lost my.
There is a question in the chat.
Yeah.
Isn't the normal vector below the sheet pointing downwards?
Is the normal vector in the what? Say it again.
Isn't it the normal vector below the sheet pointing downwards? I think that's maybe a question in which direction your normal vectors, according to your picture, I don't know, were pointing.
It does, well, really, we don't care about the normal vector. The normal vector determines the slope s comma t, from which, and that determines the z. Really, we want to add points which have the same z value together. So it doesn't really, the direction of the normal vector doesn't matter. It's only the gradient of the surface at that point. Can everybody see my screen? I feel like I don't know if I'm on my desktop or the screen. Are we back?
Yeah, we can see the theorem of Ampere on your screen.
Okay.
There is also another question from Fabio, which is, can this procedure be extended globally?
Yes. Well, the Euler-Lagrange equation is a local equation, right? And it tells you that any minimizer, right, has to locally satisfy a certain equation. And this is just a consequence of that equation. So if everything is analytic, then you can extend your solution analytically to any arbitrary domain until you reach some sort of natural boundary of until it stops being analytic.
Yeah, I meant this procedure of combining 2 solutions. You said it's local, but it gives also a global solution when you combine.
Yes, you can, right. So you start with a local solution, you analytically continue, and for the maximal domain of analytic continuation, you will have a solution on that, an actual solution on that. It may be that when you continue, you get some sort of self-intersecting surface in R3, and then of course you have to interpret what it means to be a solution in that setting. But at least at every point on that analytic continuation, locally it will be a minimizer. Did that answer your question, Fabio?
Yes, yeah, I think so, yes, thanks.
Okay, so let's go back to our Lagrange example. Hopefully this is slightly familiar territory to many of you. I mean, we have talked about Lagrange many times during this conference. Greta was just talking about them. In this case, the conformal coordinate, you can solve, the Beltrami equation in many different ways, but here's the conformal coordinate. Here's what happens, right? I have to give you z as a function of s and t here. You take a Euclidean triangle with angles pi s and pi t and vertices 0, 1, and the third vertex is at some point in the upper half plane, and that point is the complex coordinate z. So this defines z uniquely as a function of s and t, 2 points in that triangle which I've called n. And in fact, as long as we're at it, e to the x is the the logarithm of this length here. So x is the log of 1 minus z. In terms of the conformal coordinate z, x is just log of 1 minus z, and y is log of z. Remember that x and y are those conjugate variables to s and t. Okay, so it's all a very, very pretty picture for the Lagrange-Tiling case, which, and this picture, you know, encapsulates all 5 variables that we're dealing with here: s, t, x, y, and the complex coordinate z. So, but let me remind you the Ampere equation here. Well, in fact, in this form here, in this case, when I take the z derivative of capital X and the z derivative of capital Y, they're just analytic functions, right? If I write log of 1 minus z as, you know, log of absolute value, this is like the real part of log of 1 minus z. If I take the z derivative, then the z bar part drops off. Same thing with the z bar part of y. And so that this equation here, the denominators, or the coefficients of x z bar and y z bar, are only depend on, they're analytic functions of z itself, analytic functions of z. Therefore, I can just straightforward integrate with respect to z bar, and I end up with this equation here. I simplified it. Maybe I should have done that in 2 steps, but you know, I just right, because the coefficients are analytic in z, their z bar integral and their z bar derivatives are trivial. So I could just integrate with respect to z bar, and there's a constant of integration, which is going to be an arbitrary analytic function f. This is the constant of integration, maybe multiplied by, no, this is, I think this is correct. So anyway, that's what happens when you take the Ampere equation, you integrate with respect to z bar, you get a very simple linear relation between z and x and y, except for this constant term. This constant, constant of integration, which is now an arbitrary analytic function of z. And well, if you like, you can now go back and think of this as z as a function of x and y. It's an implicit equation for z as a function of x and y once you fix f. Right? If I hand you a function f, this is an implicit equation for z as a function of x and y. I can solve for z. Once I know z, I can integrate it to get, once I know z, I know s and t by this arguments of these 2 angles here. I can integrate those to get h. And so from x, y, from this function f, I can integrate to get do one more integral and get the function h, which I'm looking for. Which, so this says that every solution to the minimizing problem for Lagrange-Tilings arises from some analytic function f here.
Rick, I have a question. So is f here a true holomorphic function, or is it something which can be like multi-valued, or, you know, something defined only locally?
Yeah, that's an excellent question again, right? Again, the Euler-Lagrange equation, this is a consequence of the Euler-Lagrange equation. So you should think that everything I'm doing is sort of a local calculation. So f just needs to be a germ of an analytic function, locally defined analytic function. But once you have the solution locally, you can analytically continue to its maximal domain of definition, and that solution you get there, right? Of course you integrate h. You have to do some integral to get h. That will have some maximal domain of definition, and that will be a global solution within that domain, whatever it is. Of course, it may be hard to determine what that domain is a priori, but it can be done. And in particular, if you're looking for the box plane partition limit shape, right, that Arctic circle, then f is going to be a square root of a quadratic polynomial. F itself will be like square root of 1 minus z plus v squared. But, right, so typically f will not be a global analytic function because as we saw in many limit shape problems, there's a natural boundary where the Arctic boundary, the Arctic boundary, in fact, where the limit shape stops becoming analytic. Okay, so I just want to say one word about this terminology. Darboux integrability is a term which is used to say, well, what it means is that there's an sort of explicit solution to the PDE given in terms of some input, which is an arbitrary analytic functions, arbitrary functions. So just like in the minimal surface case, right? Remember the minimal surface case, we had this Weierstrass, where was that, right? We had this Weierstrass parameterization of minimal surfaces. You put in some arbitrary analytic functions and you get a solution to the variational problem. This is also this is what Darboux integrability means. And that's what we have here as well. I didn't write the final form, it's a little bit complicated, but it just involves some integrals of f and so on. All right. Let me, I don't want to go too fast or I'll run out of materials. So feel free to interrupt. Let me change subjects for a few minutes and talk about Kappa harmonic functions, which are going to be important in this subject. What is a Kappa harmonic function? So let's start with.
So Rick, before you go further, there's a couple of questions in the chat about this function f of z, I think. So whether it depends on the boundary values?
Oh yeah, of course. That's something we can certainly try to address, right? This is, right? What I said is you take an arbitrary analytic function and you get a solution. However, you know, that's not the problem we set out to solve. The problem we set out to solve was start with this particular Dirichlet boundary conditions on some domain, find the solution in that domain. Now, you have to do something else to figure out which f will match your boundary conditions. Right, so that's going to come up in a few slides. So ask me that question again in a few slides, and if it hasn't been answered by then. All right.
Also, there was another question whether this analytic function f, is there some special properties like convexity or something about this function f?
No, arbitrary analytic function f.
Okay, no more questions in chat.
Am I right? Let's see, let me think. No, I mean, certainly a generic analytic function f will work. I'm wondering if there's some, I mean, you might have to, something will go wrong if f has a critical point, for example, possibly. But away from singularities, then I think you're okay. Okay, so what's a Kappa harmonic function? Well, let's let Kappa be a function on the positive real valued function on the plane or some domain in the plane. And we're going to think of Kappa as a conductance function for a sort of electrical field on the plane, right? Imagine that your XY plane is made out of copper, a copper sheet, but maybe of varying thickness, or maybe there's some impurities in the copper that make the flow of electricity go, you know, slower or faster depending on this function Kappa, right? So Kappa is a conductance. And in this setting, we're going to call a function Kappa harmonic if it satisfies the following equation. You take h, your function, you look at its gradient. So if it was harmonic, you would just take the gradient and then the divergence. But you're going to take the gradient, you're going to multiply by Kappa first, and then take the divergence of that. So if you'd like to, alternatively, you can write d star Kappa dh equals 0. So this operator here, divergence of Kappa times gradient, let's call that the Laplacian with conductance Kappa. All right, so in particular, if Kappa is constant, it's just the usual Laplacian. But we're interested in Kappa having some variation. If you like to think about random walks or Brownian motion associated to a Laplacian, this is also a you can expand this expression out and you will get kappa times the usual Laplacian, but then there's an extra applied to h, and then there's an extra term which involves the gradient of h dotted with the gradient of kappa. So another way to write this equation is to write it out like this: the gradient of h, sorry, the Laplacian of h times kappa plus gradient of h times dotted with gradient of kappa equals 0. And if you like, you could think of this as having a usual Laplacian with the drift, but the drift is given by this quantity gradient of kappa over kappa. And I just put a sort of a simple one-dimensional example here. Imagine you are doing a random walk on the integers here. This is the integers, but there's a sort of a geometric, the conductance is a geometric series, right? 1, c, c squared, c cubed, and so on. C inverse, c minus 2. So the wires are getting sort of exponentially thicker as you move to the right. So then if you try to do a random walk, the rule is that the next step of your random walk is proportional to the conductance. So if you're at a point, you go to the right with probability c over c plus 1, and you go to the left with probably 1 over c plus 1. So the net effect of having this sort of exponentially growing conductance is that your random walk has a constant drift to the right, which is sort of analogous of this quantity here. And of course, we're dealing with a continuous setting here, so you have to imagine a Brownian motion with a drift depending on this gradient of kappa. All right, so what does this have to do with with our gradient variational problems? What we're going to do is, so we start with the gradient variational problem. It's got a surface tension sigma. We're going to let kappa be the square root of the determinant of the Hessian matrix. Right, we saw that the determinant of the Hessian was playing some important role in the relationship between x and t. In fact, the ratio of the z derivatives of xz and tz was, in fact, square root of the determinant. Right, this was our equation which we found before. If we rewrite this equation in terms of real coordinates, right? In fact, I did it over here, right? This is, if I multiply by 2, then x, the z derivative of x is just like xu minus I xv, where u and v are the real and imaginary coordinates of z. And this is minus I kappa times tu minus I tv. So you can equate the real and imaginary parts here, and you find that xu xv is a rotation by 90 degrees of tu tv, rotation followed by multiplication by kappa, which I rewrote over here. So what this equation means is the sort of magic property that on the z plane, the gradient of t and the gradient of x are rotated one from the other by 90 degrees, and one is scaled from the other by kappa. So you take the gradient of t, multiply by kappa, rotated by 90 degrees, that's what this star is supposed to mean, and then you then that's how you get gradient of x. Okay, but then if you apply the divergence, right, of course, that means that kappa grad t is a rotation by 90 degrees of a gradient of a function, so it has 0 divergence. So in particular, if you apply the divergence operator, you get 0. And the conclusion is that t itself is a kappa harmonic function. Right, so this equation implies that t is kappa harmonic, and in fact, s is also kappa harmonic for the same reason. Right, these two variables, now we're thinking of these as functions of the conformal coordinate z, and I apologize, I don't know, once again, for having 5 different coordinates for you to juggle in your head. But now we're writing everything in terms of the function z. Okay, z is our conformal coordinates, our favorite coordinate. We're going to try to rewrite everything in terms of z. And when we write t and s in terms of z, we find that they are kappa harmonic. And in fact, so are x and y. X and y are also kappa harmonic. Well, no, sorry, they're 1 over kappa harmonic functions. They are the harmonic conjugates of t and s respectively. Right, so this equation is somehow equivalent to the fact that x is a kappa harmonic function. That's in fact the definition of being kappa harmonic conjugate to T, which makes it a 1 over kappa harmonic function. I hope that's okay. I know this is, you know, not the kind of tools that you're used to dealing with, but it's just some elementary vector calculus here, but with some complex variables thrown in, and I appreciate that always makes things difficult, but feel free to ask questions. That's what we're here for. All right, so here's the main theorem of today, and I proved already that S and T are kappa harmonic functions. It's also true that this third function, you take the height function H, any solution to the minimization equation, you subtract the Sx plus Ty, right? This is the intercept, if you like, of the tangent plane. These three quantities are all kappa harmonic functions with respect to the conformal coordinate Z. Kappa harmonic functions of Z. But okay, so and the corollary here is that if you want to write, if you think about the graph of H, right? H is your minimizer. Well, H is the function whose graph is the minimizer. This minimizing surface, graph H, is the envelope. With the envelope of its tangent planes, but all those tangent planes are what we call kappa harmonically moving planes. That's a family of planes indexed by the conformal coordinate Z, right? And a plane in R3 looks like the third coordinate, x3, equals A x1 plus B x2 plus C, where x1 and x2 I've called x and y. So I apologize for the change in notation. But then the coefficients of the tangent plane are, of course, S, which is the x derivative of H, T, which is the y derivative of H, and C, the intercept is exactly this third thing here, H minus Sx minus Ty. Okay, so this family of planes here has coefficients which are all kappa harmonic functions of Z. Right, so I don't know how to draw in a nice way a envelope of a family of planes, so I did it one dimension lower, right? If you take a curve and you look at all of its tangent planes, of course you can reconstruct the curve from the planes, from the family of planes, and that's what's going on one dimension higher. Once you understand the set of all tangent planes, then you can reconstruct the surface from that. And the result is that this is for a general variational problem, not just the Lagrange model. All variational problems, all gradient variational problems, the solutions are envelopes of families of kappa harmonically moving planes, where what I mean by that is this expression here. Planes which are parameterized by this conformal coordinate Z, and the coefficients are kappa harmonic, where kappa is, of course, the square root of the determinant of H, the Hessian of the surface tension. Any reactions? Okay, well, for those of you just going back to slightly more firmer ground, if you go back to the Dimer model, the Lagrange model, I should say, but it happens for the general Dimer model, also bipartite Dimer model. The minimizing, so in this case, the Dimer model has a special property that the Hessian determinant is in fact not varying. It's just a constant, pi squared, right? And because the Hessian determinant is constant, kappa is constant, and therefore the kappa harmonic function is just a true harmonic function of Z. So the minimizing surface graph of H is the envelope of a family of harmonically moving planes, harmonically in the usual sense. Harmonic, right? So, but right. So I think this corollary is supposed to indicate that somehow when you write things in terms of the conformal coordinate z, everything is in some sense the friendliest possible object you can imagine. You know, the coefficients are all harmonic functions. And before I go to the last picture, let me just go to the next slide for briefly. Here's the sort of simple application. Was there a question?
Yes, so there was some question. So there was a question from Fabio, whether for theorem you only need sigma to be a c² smooth or more.
Yes, we need c² smooth, and we need the Hessian to be positive definite almost everywhere. So if you like, make the Hessian be, right, you can have a smooth function whose Hessian is positive definite, sort of not a full measure, but we don't want to deal with that situation. But all we need to do is solve that Beltrami equation, right? Whenever you can solve the Beltrami equation, then everything else follows. So if you really care about what the optimal smoothness conditions are, it becomes a little bit more complicated. But in fact, I think Gauss only did it for analytic surface tensions, but it can be done in greater generality. But you do need some ellipticity, mild ellipticity restriction on H. Okay, so yeah, so here's another picture of that lozenge tiling of a box plane partition, which I'm showing on edge here. And what you can see from this picture is that if you think about the limiting surface, the tangent planes near the boundary are in fact determined, right? Over here, you see this blue facet. That means that the tangent plane is determined all along that edge. In fact, well, be here and there and there. So because in certain situations, so what I said here, right? In certain situations, we know what the planes are at the boundary. And if we know what the planes are at the boundary, then we can just, yeah, I said it here. You can determine the limit shape by harmonic extension, right? If you know the planes on the boundary and you look at the unique family which harmonically extends the boundary values, and that will give you the minimizing surface inside, at least for the dimer model. And assuming you can Kappa harmonically extend, which, you know, I mean, the existence is easy. Depending on Kappa, it might not be easy to give an explicit solution, but right, the Kappa harmonic extension is also something reasonably well understood.
Rick, could you add more details to this box plane partition case? Like, what exactly do you need to do now to get a limit shape? So you're saying that there is a simple procedure. So can you kind of, you know, give it in a closed form? What exactly you're doing?
I can try. Let me give it a try. Let me go back to the whiteboard. So remember, so here's our, let me just draw it in this perspective, right? We have this box plane partition. Oh boy, sorry, my pen is, there we go. And remember that the z coordinate lives in this upper half plane, right? There's this z coordinate given by this triangle here. And on this region here, on each of these regions, we know what the z coordinate is. Z is either, you know, 0 or 1 or infinity, depending on your orientation. 0, 1, infinity. So well, I apologize. The thing about the box plane partition is a little bit more complicated because the map from here to the upper half plane is 2 to 1. It's a branch cover, branched over the origin here, which makes it a little more complicated. But the point is that there's these 3 regions. Let's call them 1, 2, and 3 here. Between 0 and 1, between 1 and infinity, and between infinity and 0. And those 3 regions sort of get collapsed. Along the boundary, those get collapsed to these 3 points. but since it's a 2-to-1 map, they get these 6 points. Oh yeah, so this was wrong. I didn't mean to put zeros, ones, and infinities here. I meant to put them. No, that was right. I was right. I apologize. 0, 1, infinity. Right. So the line between 0 and 1 gets collapsed down to this point. But so you know, but we know the coordinate of the plane here. The tangent plane, yeah. So the tangent plane at this point is determined, and let's see, what do we need to do? You're putting me a little bit on the spot, Vadim, but right, the point
you can continue and we can discuss later. I mean, it's not.
Right, there's some right, the tangent planes are it's not well defined at this point. They sort of there's a non-smoothness of the limit shape at that point, and that's what's causing me trouble. Okay, let me go on. Sorry, lost my slide again. There we go. Oh yeah. In this situation, what is the what should we expect the fluctuations to be? And previously, in Hugo's situation, he was on a torus. Everything had some translation invariance. You expect the Gaussian free field, but because the kappa in his case was just constant throughout his torus. But if you have a domain with non-flat boundary conditions, then the z value is going to vary over the domain, and therefore you are not going to see a Gaussian free field. You're going to see a kappa Gaussian free field, which is the appropriate Gaussian object for the Green's function, the kappa harmonic Green's function. So it's not going to be just like in the general Lawson-Steinle case, the diffeomorphic image of a Gaussian free field, as long as if I understand correctly, it's going to be some slightly different object, right? The Gaussian free field with a varying conductance, which is also not a very difficult object, I don't think. But as far as I know, nobody has sort of studied this object and in its own right. And this is, by the way, just a prediction. I don't really have any way of handling these fluctuations with the current technology. Okay, how are we doing on time?
Rick, before you continue, there is one more question in the chat. So it is about either a discriminant with a given interpretation in each one of these model equations. For instance, in the Gauss model and Beltram equation, the expression within the radical, and in other models, the ratio of x divided by xz and so on, based on your studies or any simulations made.
Let me look at the chat. That's a lot of material. I think that I don't have a good understanding of that question. Maybe we can discuss it afterwards, Anthony. I don't know how to answer that question right now.
So there's also another question of Fred, whether Gaussian free field predictions are known in some very specific integrable cases.
As far as I know, only in the Lawson-Steinle cases where the determinant is constant. Then for many, I would say many boundary conditions have been worked out where you get an actual Gaussian free field in the Dimer model versions. But as far as I know, no model with varying kappa has has the fluctuations worked out. I'd be happy to be, if someone knew some such model. Okay, here's one more little trick, which is going to be relevant for tomorrow's talk. If I take another square root, which is let psi be the square root of kappa, which is now the fourth root of the determinant of the Hessian. If we replace h with h times psi, then that kappa harmonic equation becomes a Schrodinger equation. Looks just like this. So now h tilde is our new function. H is the old height function, and I'm just multiplying it by the fourth root of the determinant, and then it satisfies the Schrodinger equation. This is a trivial one-line exercise. You can do all this yourself, where the potential term now. So this is this usual Laplacian with respect to z minus q applied to h tilde equals 0, where the potential q is Laplacian of psi over psi. And so for the 5-vertex model, which I will introduce tomorrow, if not today, depending on time, this is just a simple special case of the 6-vertex model. It turns out that this function psi is harmonic with respect to the variable z. So the Laplacian of psi is 0, and therefore, under this simple substitution, h tilde is just a harmonic function in the friendly harmonic sense, constant conductance harmonic function. So kappa harmonic functions are all of this simple form, a regular harmonic function divided by the fourth root of the Hessian determinant. So in this sense, kappa harmonic functions are actually quite friendly. They're just harmonic divided by psi. Therefore, we can also describe explicit limit shapes for the 5-vertex model, just like we did for the Dimer model. So this is a version of Darboux integrability for the 5-vertex model. Right? You can write an explicit integral equation for all limit shapes. We still have the problem of matching the boundary conditions to the harmonic function, but in principle, at least, there is a harmonic, an analytic function describing every limit shape, and you can write an explicit integral formula for that. This is, by the way, something we worked out. This is like the start of this whole theory, which is that we worked out the 5-vertex model, and I'll explain what we did next time. We discovered that we could integrate those equations explicitly, and then by working backwards, we discovered all this envelope business. Okay, well, it's been an hour, and this is a pretty good stopping point for me. If people would like to ask questions, or maybe I'll stop here.
Okay, good. Thank you very much. So, do we have any additional questions for Rick?
So there was a comment in the chat by Fabio that with Giuliani and Mastropietro, they proved GFF for interacting dimers. I wonder whether there is a non-trivial kappa there or not. So maybe Fabio could say that.
Yeah. In that case, okay, let me make it more precise. So that we prove these fluctuations only in the case where you take the translation invariant measures. So we don't have non-trivial limit shapes. But indeed, kappa depends on the slope in that case. And it's, I mean, the proof works really for small enough perturbation around the free fermionic case. I mean, I cannot quantify how small, but it's not, yeah.
I guess that's saying that if there were boundary conditions with non-trivial limit shape, then kappa would not be constant in that case, right?
That's correct. We have it depend. We can It is dependent on the slope. So then what you say is true, yes.
Do we have any other questions, comments, or anything?
I should say that the paper here is available in the archive about what I talked about today.
Okay, perfect.
I actually have a question. Okay, maybe it's a question for tomorrow, I guess. But in the 5-vertex model, that is determinantal, right? Even in the generic case, or?
No, it's not determinantal. You need beta ansatz to solve the 5-vertex model.
It's, okay.
I'll explain tomorrow. That is indeed a question for tomorrow.
Yeah.
Okay, so if there are no more questions, then that's it for today. Tomorrow, Rick is giving a last lecture in the afternoon. And for today, that's it. So thank you very much, Rick.
Thank you.
And so tomorrow we'll start at 11 a.m. Eastern time with Hugo's last lecture, then Greta and Rick. See you tomorrow.